Hello students, welcome to Chatterjee Academy. So today's session is for the conservation of mechanical energy in case of simple harmonic motions. So I hope that all of you having basic idea about simple harmonic motions. So simple harmonic motions, here we are having the time dependency, right? Okay. And in these motions we are having the restoring force, and the general equation of the simple harmonic motion here, force F is equal to minus kx, right? F is equal to minus kx, where k is equal to, omega and m, right? So it will be m omega square, spin constant. So this is the very basic thing, I hope you know. And for simple harmonic motion, what happens that if this is the center of oscillation mean position, here we'll be considering x is equal to 0, here x is equal to a, and here x is equal to minus a. So there are three positions, and these are the extreme positions. So in these positions we know that velocity is max, and in these positions velocity is 0, v is 0. So kinetic energy will be 0 at the extreme positions, and in the extreme positions total energy will be the potential energy. So I will show you the expression by which we can prove that at any point the summation of the potential energy and the kinetic energy is conserved, and that is independent of time. Okay, so let's go and prove that, and we will take the example of spring at the end, so that it will help you. So x is the displacement of the particle and F is the restoring force. Fine. So this is the equation of the simple harmonic motion. Then first of all, let's draw the work done for a displacement of dx, right? So we are doing a work done for the dx displacement of the particle from x to x plus dx, let's say. So work done will be w is equal to, that f dx, right? So dw is equal to what happened, f dx. F is equal to minus kx dx. So I hope you can able to see it. dw is equal to minus kx dx. dw is equal to minus kx dx. Okay. Now total work done in moving an object from 0 to x, it will be the integration, right? So minus 0 to x kx dx, okay, kx dx. So here we are receiving kx dx means we are getting half k x square, right? Half k x square. So this will be the work done with the minus sign. Work done with the minus sign. So why this we are coming the so we can able to calculate the work done, which is the displacement dependence. Now we will correlate the potential energy with the work done. So potential energy, we know that it is the the change in potential energy from x position, 0 position to x position, that is the negative of the work done. So we have received the work done is F is equal to W is equal to minus kx square, right? Minus kx square. So what will be the change in potential energy? Now this will be ux minus u0 will be negative of the work done. That means half kx square, right? So that is the potential energy. So we receive the potential energy between the x is equal to 0 to x is equal to x, right? So it will be treated as an ux is equal to half kx square. This is the potential energy expression. Now k is equal to, we know that m omega square. So potential energy U will be half m omega square x square. Half m omega square x square. So this is the expression of the potential energy, right? Now we'll show you the displacement equation, right? So what is the equation of the displacement here? That is x is equal to a, let's say, sine omega t plus phi. So velocity will be a omega cos of omega t plus phi. This is the velocity expression and this is the displacement. Now we will utilize this to here. Now potential energy is half m omega square x square. Now what is kinetic energy here? So kinetic energy is k is equal to half m v square. So half m a square omega square cos square omega t plus phi. Clear? So you got the kinetic energy. Now if we add both potential and the kinetic energy, total mechanical energy. So let me zoom it for more clarity. So total mechanical energy E is equal to U plus K, the potential energy plus kinetic energy. So U is half m omega square x square. So x is the expression here now, and kinetic energy is the half m v square, right? So it will be, if we replace x and v with the sine and cos, it will be half m. Okay. Then we'll just replace it omega square, so it will be sine square omega t plus phi plus cos square omega t plus phi. Okay. So this one will be 1 sine square theta. We know that sine square theta plus cos square theta is equal to 1, right? So it will be half m omega square a square. Yeah, one more part, a square we missed here, right? So this is the total energy. So if you see that total energy is independent of time, total energy is independent of time, right? You can see here. So total mechanical energy in case of simple harmonic motion is independent of time, right? So same thing we can show it in the case of the spring. Let's take an example of a spring to just have some experimental verification what we did now. Okay, so let's take a spring which is performing simple harmonic motion. So there is a block of mass m with a spring, right? Now let's say this is an x is equal to 0 position. Now we'll take this from here to a max position, x is equal to a. We'll stretch it. Again, it will come back, right? The next one we can draw like here, it's an extend, it's a stretch part. Again, it will compress, right? Compress with this in this position. So if this is x is equal to 0, this is x and this is x is equal to minus a. Right. So the spring is doing the simple harmonic motions under the restoring force, the elastic force of this spring, the elastic material. Let's say this is an elastic material, same like spring. If we stretch this one, this is a rubber, like it is having a high elasticity. If we stretch this with a force, the moment we are, let's say it's a mean positions, we are stretching it, what is going to happen that we are receiving the opposite force. If we release it, it will come back. If we release it, it will come back. That means because of the restoring force. Whenever we are stretching and we are doing the x displacement like this, so restoring force we will try to make it in the original positions. So that is due to the elasticity, right? So same thing happened in the spring. The spring is trying to come back to the original positions and simple harmonic motion is going on. Following the equation, F is equal to minus Kx. When x is equal to 0, what happened? That we know that x is equal to 0, velocity maximum, right? And when x is equal to a, velocity is 0. So in case of spring, when x is equal to a, total energy will be what? Half m omega square, a square, right? Total energy in x. But similarly, when x is equal to 0, total energy will be same. That is converting to the potential. So yeah, at this position, x is equal to a. Here it is the total energy is the potential energy, because x is equal to a, v is equal to 0. So there is no kinetic energy in the maximum positions in case of simple harmonic motion of spring in anywhere. But when x is equal to 0, the velocity is the maximum. Velocity is the maximum, right? So at the center of the oscillation, it is having the maximum velocity. At the maximum positions, the velocity is 0. It will be having the total, the potential energy, and acceleration will be maximum in the max positions. Clear? So I think it will help you to understand the simple harmonic motion and its conservation. It is time independent. Okay. Thanks for watching. So please reach us and follow our channels to see this kind of conceptual sessions. Okay. And also please subscribe to Chatterjee Academy. You will get lot of sessions like this. Okay. Thank you.